Okay. So that is kind of just the very brief introduction of the definitions that we're going to be dealing with, relative and absolute minima and maxima. Now, a big part of calculus is if you have a function, trying to find out not only what are the minimum and maximum values, but also where they occur, right? It's actually a very important application. Pretty much, I mean, every single quantitative field has some sort of application from calculus, and this is by far the most common application, finding maxima and minima. Okay, so there are two theorems that kind of guarantee how we can actually find maxima and minimum, because some functions do not have maxima or minima. We will actually look at an example in just a second, right? I mean, you might want to actually think about that. How can a function not have a maximum or minimum value? Okay, so the main theorem that we are looking at in this section is what is called the extreme value theorem, which I'll often abbreviate as EVT. Now, the extreme value theorem gives you some conditions on a function that guarantee that that function has a maximum and minimum. Again, not every function has a maximum and minimum, but this theorem guarantees when certain functions do. And there are three conditions. There's one condition on the function itself, and then there's two conditions on the domain of the function, which is still part of the function, but it's not really on the values of the function. So first of all, if the function is continuous, right? So suppose f is continuous, and then the domain has to satisfy these two conditions. Suppose f is continuous on the closed bounded interval AB. So again, notice the three conditions, right? The one condition is that the function is continuous. The second condition is that the interval is closed. And then the third condition is that the interval is bounded. If you're not sure what closed means that both endpoints must be included in the domain, right? So I have a square bracket on both endpoints. Bounded means it's not going off to infinity. So for instance, the interval 1 to infinity is actually still closed, but it's not bounded. The interval just kind of goes off to infinity. It has arbitrarily large values in the domain. So if you have those three conditions, then you are guaranteed that the function has a maximum and minimum. Then the absolute min and max of f on this interval exists. So that's actually really nice, right? That if we deal with continuous functions on closed bounded intervals, we are guaranteed to have an absolute minimum and maximum. And for the most part, those are the types of functions we deal with. Even if in practice we might come across functions that are not continuous, a lot of times we can approximate those functions by continuous functions. So this theorem actually is very, very useful. So probably in the homework at some point, I'm going to ask you, well, what happens if you drop one of these assumptions? What if the function is not continuous? Or what if the domain is not closed? Or what if the domain is not bounded? You know, give me an example that shows that you are then not guaranteed the absolute minimum max. Let's look at least at the first condition. What if we do not assume that the function is continuous, right? So right now, I just want to show you why all three of these conditions are necessary. If you drop any one of these assumptions, you are no longer guaranteed absolute min and max. You might still get them, but you're not guaranteed them. This will be very important when we start optimization, because for optimization that we do for the exam number 6, the last exam, we actually will often deal with continuous functions, but the interval is neither closed nor bounded. So a big issue that we're going to have to deal with is how do we even know the min and max exist in the first place? But for now, we won't have to do that. So let's look at one example. What happens if f is not continuous? So what can go wrong if f is not continuous? Okay, so the domain of this function will still be a closed bounded interval, just the function won't be continuous, and we're going to see we are no longer guaranteed a min or a max. You can actually fail to have both. So here's 1, here's 5, Here's say A, here's B. So the domain of this function will be, say, A to B closed. So there we go. So this function has domain AB, right? So conditions 2 and 3 are true. The domain of this function is a closed and bounded interval, right? You can check that every single x value in this interval does have a y value. I mean, there are open holes, but every single x value does have a y value. Now, does it have a minimum? Does it have a maximum? There is no minimum and there is no maximum. I should say, if we don't have a qualifier on max or min, we always mean absolute, but let me actually write it there. So no absolute min, no absolute max. So that's a function. That's an example of a function that has no min and no max. And what's the problem? Why does this not contradict the extreme value theorem? Well, this function is not continuous. So this theorem did not guarantee you that the absolute minimax existed. So once you drop one assumption, the condition no longer, the conclusion no longer necessarily is true. Okay, any questions so far? Because we're now going to then start talking about how do we actually find max and mins. Local max and mins pretty much always exist. Okay, it depends. If you go by the textbook's definition, this function also has no local min or max, because the local min or max, the local min, there is a local minimum at, say, x equals a, right? That's a local min right there. But according to your textbook, that's not what's it called? It's not a local minimum because it occurs at a boundary point, right? Same thing for so this is actually a local min if you go by real math. And at x equals b, we actually have a local maximum, right? This is the biggest y value if I look at only a small interval around x equals b. But your textbook does not allow these to occur at boundary points. Is it possible for a function to have no local mins, no local maxes, no absolute mins, and no absolute maxes? It turns out yes, but those types of functions are well beyond the scope of this course. They're very pathological. If you're interested, there are these types of functions that actually are useful, though those types of functions, they're actually used to model, say, things that have random fluctuations, like stock prices or the position of, say, a pollen particle in water in a Brownian motion. So actually, these types of functions that have very pathological are still useful.